I'd like to thank the organizers of this meeting for the invitation to be here today and share with you this topic. And also, I would like to thank all of you online attending this meeting and attending my talk. It's my pleasure. So today, what I selected for today is about a nanoring morphology for magnetic nanoparticles and their application in magnetohyperthermia. So here is my agenda for today. So I will show you typical nanomorphology for magnetic nanoparticles, and the unusual one, which is the nanoring. And then I will step and briefly describe the synthesis of magnetite nanorings. And then I will show you some unique features of nanorings. And finally, their application in magnetic hyperthermia. And I will come at the end to conclusions of this talk. So, if you look at the literature, typically spherical morphology is the most standard you can find on most of the nanomaterials. In case of iron oxide phases, you also can find the cubic morphology. So these two very nice transmission electron microscopy. And then you can see also in the inset, you can see the particle size distribution. So the typical size is below 50 nanometer. So you can see a very nice particle size distribution, very nice uniformity in this iron oxide nanoparticles. This was a very nice piece of work done by colleagues in France in the Strasbourg University. So, although most of the morphology you can find in the literature is spherical, we came about with nanorings. So here are typical transmission electron microscopy of the nanorings I'm going to talk today. So it's very nice nanorings, and you can see in this particular case, we have a mean internal diameter and a mean external diameter of these nanorings. On the right-hand side, you can see the particle size distribution, or the size distribution of the internal diameter, which is about 42 nanometer, and the external diameter in blue, which is about 81 nanometer. It means typically the thickness of the ring is about 20 nanometer. And if you look at the high transmission electron microscopy right in the center, you can see the typical interplane distance, 104 plane interplane distance, which is 0.26 nanometer, which is typical of the magnetite phase. Besides this characterization, we performed several other characterizations to confirm that indeed the phase we are talking about is magnetite. So, shortly, how was the route of fabrication of the magnetite nanorings we took? So the first step is to prepare the hematite nanorings. Actually, the hematite nanorings is described in the literature. So we start with a aqueous solution of iron 3, and actually is a low pH aqueous solution. So we stir for a few minutes and then perform the hydrothermal treatments, a long hydrothermal, 48 hours, well, 220 degrees centigrade, the temperature. And after 28 hours, you can open up the system and you will find the hematite nanorings. So this was the first step. In order to prepare the magnetite nanorings, we take the hematite nanorings and treat it with iron 2, 1 molar iron 2 chloride, actually. So we believe that the iron 2 ions just decorate the hematite nanorings, and then we perform the hydrothermal treatment. It's a comparatively a short time, 8 hours only, and a very mild temperature, 9 degrees centigrade. So after 8 hours, we open up the system, wash, and finally we could characterize the magnetite nanorings, not only in terms of morphology, but also in terms of phase and magnetic properties. This process is described in this publication. And in this publication, we emphasize the novelties of this route. First point, which is this was the first fabrication of magnetite nanorings, pure phase, no side phases at the end. And then the second important point, we started with hematite nanorings, which is a very standard process you can find in the literature. And the third important point, so we performed a mild and short hydrothermal treatment to finally end up with the magnetite nanorings. So what are the unique features of nanorings? Let me emphasize one which is very important for the application in magnetic hyperthermia. So the nanorings, they have a real and very nice spin vortex system, as you see on the left-hand side of my slide. So this picture shows how the orientation of the spins inside the system. On the right-hand side, I can show you a very interesting aspect. If you take a hollow cylinder versus a solid cylinder, so in the hollow cylinders, you have a real magnetic vortex. However, if you look at the solid cylinder, you don't have a perfect magnetic vortex. So you have a net magnetization along the z-axis. What are the key features of the nanorings? So it is a perfect spin vortex system. And however, it has a open hysteresis cycle. If you look at the on the left-hand side, the hysteresis plot, even at room temperature of the nanorings, you can see that we have a very unique presentation of the hysteresis cycle. So it almost closes at zero field. However, it opens up a higher value of applied external field on the positive branch and negative branch, and finally it saturates. Okay, what are the important outcomes of a nanoring? Very important for the biomedical application, particularly the magnetic hyperthermia. First point is that we have a minimal dipole interaction. And this is a very important point as far as the biomedical application is concerned. And that is if the nanorings, they minimize the dipole interaction. It means that agglomeration once inside a biological system is minimized. This is a very important point. The second interesting point is that the nanorings actually, it maximize the AC field interaction. And this is a very important point for magnetic hyperthermia. So let's turn to the hyperthermia therapy. The first aspect of hyperthermia therapy is that it is not actually a novelty. It's a very old treatment, actually. It was proposed before Christ, so it was proposed for the Greek physician Hippocrates II. Important to mention that we had actually a long line of Hippocrates from the first to the fourth. So the most famous is the Hippocrates II. So here is the statement in Latin, and I will translate this to English. So it says, those diseases which medicine do not cure, knife cures, and those which knife cannot cure, fire cures, and those which fire cannot cure are to be reckoned whole incurable. So the hyperthermia was used actually since the ancient times. But today, the modern hyperthermia we can perform using nanoparticles. And actually, we have two main directions to applicate for the application of hyperthermia. One is the magnetic hyperthermia, for instance, using iron oxide nanoparticles. And so it is the application of AC magnetic field. And the magnet hyperthermia has actually two important, very important characteristics. First, it allows you remote manipulation of the magnet nanoparticles. So that is allow us to bring the nanoparticles in the right site. The second aspect, which is equally important, is the remote heating. You can apply the AC external field, and regardless the site where the nanoparticles are in a biological system, it responds to the external AC field. The other way to perform the hyperthermia in these days is using optical excitation. In this regard, we use actually metallic nanoparticle, like gold nanoparticle, and then you apply infrared illumination. So if you compare these two approaches, you will see that the optical hyperthermia does not allow you remote manipulation. Regarding remote heating, actually is very much limited. So it depends on the penetration of the infrared light. So between these two, it seems that for hyperthermia in clinical treatment, the most promising one is actually the magnetic hyperthermia. So the magnetic hyperthermia allows you to perform remote manipulation. It looks like a magnetic pliers, actually. The magnetic force acting on the magnet nanoparticle scales with the DC susceptibility, the particle volume, and the gradient of the magnetic field. So you can manipulate the nanoparticles once you have a gradient of external magnetic field. Regarding remote heating, the rising of the temperature scales with the AC susceptibility and the AC frequency and the AC amplitude of the field. Of course, it scales with the time you are applying the AC external field. So these are the two important features of the magnetic hyperthermia: the possibility of remote manipulation and the possibility of remote heating using AC applied external field. So if you look at the typical, if you look at the typical hysteresis cycle, we have two opposite directions or opposite conditions. In the left-hand side, we are on the slow magnetic field reversal time. So the typical time of reversal of the external field is higher than the typical relaxation time. In this case, you have a closed hysteresis cycle. However, if you reduce the reversal time, or if you perform the fast magnetic field reversal, increasing the frequency of the AC field, you open up the hysteresis cycle. And the heat dissipation actually scales with the area of this open cycle. And that is exactly what happens with the nanorings in our case. So nanorings are very effective in this regard. So to look at the magnetic hyperthermia, what is the big challenge of this technology? So here is one a very interesting result. It was an experiment performed by colleagues in Vienna, in Germany. So they injected magnetite nanoparticles in a tumor. You can see a small picture on the right-hand side. You can see a tumor on the side of this mice. So they injected dextran-coated magnetite nanoparticles in the tumor, and they applied external AC field for about between 5 and 6 minutes. And then they implant some thermocouple, not only in the tumor, but also a reference one in the rectum of the animal. And then you can see the temperature raising as a function of time in the main plot in this figure. And you can see that the reference temperature scales below 30 degrees centigrade. However, the tumor temperature raises up to a little bit over 70 degrees centigrade. So this technology has a border, very important border in terms of temperature. And this means a very big challenge. So the border is around 43 degrees centigrade. So we want to operate the magnetic hyperthermia in the asymptotic temperature around 43 degrees centigrade. Why is this? So above this border, around 43 centigrade, we perform thermal ablation, actually. So we perform necrosis in the cells, in tissues. However, around 43 degrees centigrade, we perform thermal sensitization, and that leads to cell apoptosis. This is the main point that we want to target. Actually, we want to use magnetic hyperthermia to trigger the apoptosis of the cells. What is the difference, actually? So when you do thermal ablation, operating magnetic hyperthermia higher than 43 or 45 degrees centigrade, you break up the cell membrane, actually, and then you trigger necrosis in the tissue. It's not a very good option. On the other hand, if you operate the magnetic hyperthermia technology around 43 degrees centigrade, you perform thermal sensitization, which means you damage some organelles in the cell, like mitochondria and lysosomes, and then the cell triggers the self-death, which is apoptosis. This is the main target in this technology. So to perform this technology and use it in clinic, it's very important to write down protocols that the magnetic hyperthermia will be applied in the asymptotic temperature or operating temperature around 43 degrees centigrade. We can achieve this goal in two different directions, or the combination of the two. First, in terms of instrumentation. So we can use a temperature sensor in the site, for instance, in the tumor, and we can control electronically the AC applied field in terms of time, frequency, and amplitude in such a way that you have a control of the temperature, the operating temperature around 40 degrees centigrade. On the other side, we can also design samples, magnet nanoparticle samples, in terms of material, in terms of phase, shape, size, and surface coating. maybe the combination of these two directions may provide you the best control of the magnetic hyperthermia treatment. So just to show you, in the case of the nanorings, this slide shows you the application of magnetic hyperthermia with the nanorings I showed you before. And here on the right-hand side, we see the rising of the temperature as a function of time. This time is the application of the AC field. And we performed all these 4 experiments, keeping the AC frequency at 330 kilohertz. And we change the amplitude of the AC field from 100 Hertz up to 240 Hertz. And then you can see that between 200 Hertz and 240 Hertz, the asymptotic or the operation temperature is exactly in the range between 40 and 45 degrees centigrade. So we can manipulate or modulate the amplitude of AC field to keep the operating temperature, the desired operating temperature. So all these plots, you can fit them by using the box Lucas model, which is the temperature scales with the operating temperature and time. So this is the typical relaxation time of the magnetic hyperthermia. So if this data shows you, you can write down your protocol based on the response of the magnetic nanoparticle. So why, in this case, the nanorings are important? They are important because, as I said before, the interaction of nanorings with the AC magnetic field is very strong. This is the first point. And the second point is agglomeration of the magnet nanorings is extremely minimized. So this is a very important point for the application of magnetic hyperthermia as a therapy. So my main conclusions about this talk today. The first one is magnetite nanorings provide reduce agglomeration and suspension. And this is a very important point. If you are injecting a suspension of magnet nanorings into the body. So the second point is magnetite nanorings provide controllable magnetic hyperthermia operating temperature. So you can play with the AC magnetic field and the amplitude of the magnetic field. The third important point is magnetite nanorings provide safe magnetic hyperthermia operation for clinic protocols because you can simply control the operating temperature, which is a very important point. So to be able to perform apoptosis and not necrosis. And the fourth point, magnetite nanorings require low AC magnetic field frequency. So it's below 500 kilohertz and small amplitude. So you can operate below 250 Hertz in terms of AC field amplitude. So I would like, again, to thank the organizers of this meeting. It was my pleasure to be here today. And also, I would like to thank all of you online attending my talk. And it's my pleasure to share these ideas with you. So if you have any question, I'll be happy to take the question. Otherwise, if you want to contact me, here is my email address in the bottom of this slide. So you can copy it and keep in touch at any time. Thank you again. Thank you so much.